Good morning, everybody. Good morning, Wabash. Um, this morning I need to do census, which is basically to check attendance and get the info to the registrar that, yes, you actually are alive and exist. So I'll go through that first. Those of you guys who are online, please just hop either in Discord or the Twitch chat so that I'll know that you're quote here end quote. Um, all right, so Mr. Adams, Mr. Borden, are you back with us yet? Where? Ooh, I miss you. It had been slow. Monsieur Cook, Monsieur Dreysens, Monsieur Early, Mr. Egan, you should be online somewhere. Um, I can hang on one second, guys. I can't see the chat. Okay, Mr. Egan, you're here. All right, gotcha. Mr. Goss, I'm gonna butcher this. Andrew Gorsich, you should be online. So type in the Twitch chat if you're actually here. Mr. Jonathan Hall, Mr. Richard Hall. Uh-huh. Excellent. Mr. Hargraves, yep, I see you. Mr. Hidalgo, excellent. Mr. Hill. Oh, and I'm assuming that's Drew. Okay. Où est Monsieur Hill? Monsieur Hill est disparu. Monsieur Lee or Ivy. Nope. You guys should be online. Monsieur Jax. Excellent. Monsieur Knetkar. Bonjour. Monsieur Kennett. Kennett. Okay. Monsieur Miller. Où est Monsieur Miller? No, Monsieur Miller. Monsieur Nagaba. Present. Monsieur Pine. Who is me? Okay, Monsieur Rotterman, Monsieur Runge, Monsieur Sanchez, Monsieur Canton or Terry, Monsieur Truong, and Monsieur Valera de Villa. All right. So let's see. So who do I not have? Monsieur Borden, he should be here physically. Mr. Hill, Mr. Ivy, and Monsieur Miller, and Mr. Truong. Sound off someplace. Thank you, Mr. Miller. Okay. All right, well, let's get to it then. So let's kind of recap from last time. What we were looking at was, if Twitch will switch over here. There we go. So last time we were looking at what do you do to notate a bit pattern. And the convention that we use for this stuff is to take it in 4-bit chunks. So if you've got a much longer number, then you just take it in successive 4-bit increments until you are finished. And the system that we use is called hexadecimal because it's base 16. And so it's getting a little bit chopped off there, but then all ones is that, well, here, I'll just cut off the all zeros because that should be kind of obvious. So this is the pattern, right? And in a sense, you can think about each of these 4-bit patterns and each of the the symbols to the right as being equivalent. But we can also talk about what sort of these things mean numerically, right? So last time what we said, right, is that you can think of these bit patterns as being a number in sort of place value style arithmetic, where the far right position is the ones place, then the twos place, then the fours place, then the eights place, and so on, right? Just like normal arithmetic, it just goes up by twos instead of, or sorry, powers of two instead of powers of 10. But hexadecimal actually works similarly. So if, for example, let's take this number here, okay, 96 in hex, then what is this sort of numerically if we went through and thought of this as an integer of some sort? Well, is it 96? No, it's not 96, okay? And the reason is that the 9 and the 6 represent patterns in binary, not the number 9 and the number 6. What this would actually be is it'd be 9 times 16 plus 6. Okay, why? Well, where is the 6? What position is he in? Well, what's the far right position no matter what system you're working in? It's always in the ones place, okay? Then what's the place one value to the left of it? That is the, okay, in binary, it'd be the twos place. But over here, we're not working in binary. This is hexadecimal. So how many digits are there in hex? 16, okay? So what is this position? The 16's place. That's why I multiplied by 16, okay? And then whatever 9 times 16 is plus 6, okay, 100 and something, who cares, right, for right this instant, that is the actual sort of numeric value of this thing. Okay. And we can go back and forth between these things. So let me actually show you guys sort of a real world use for this. So how many of you guys have what, like an Xbox or a Switch or something like that, right? And then how do you get that thing on the Wi-Fi at school now? Yeah, you got to register its MAC address on the school website, right, so that it can connect to the Wabash IoT network, because they've switched up everything. Well, if we look at a MAC address, so for example, this is a little hard to read, so I'll just copy and paste it. Okay, right there, is the MAC address for the Wi-Fi unit in my laptop. Okay, but what do you see? Oops. Yeah, it's all in hexadecimal. Okay, so when you guys got the hardware address for your switch or your whatever to get it connected to Wabash IoT, you needed a number that looked like that. It was 6 pairs of hexadecimal. Well, each pair of hex represents an 8-bit pattern, right? And you've got 6 of them there, right? So this is a 48-bit string that is unique to the actual wireless chip in your particular device, right? So I've got 2 laptops up here. They both have different hardware addresses. Your switch has a different hardware address. The wired Ethernet port, if there is one, has a different address, right? And so you've got 48 bits to represent, and actually kind of usually the way it works is some of the stuff at the front tells you who made the chip, and then the rest of it is like its serial number, for lack of a better way of putting it. Okay, but yeah, this is a big 48-bit string. All right, so let's just convert the whole thing into binary. What is it? Well, let's do it one chunk at a time. Okay, so I've got A0, CE, C8, I'll just sort of split it up like this for the sake of readability. And the other thing maybe I should mention here is, does it matter if it's lower or uppercase? Not really. Okay, now in most instances, lower versus uppercase is something that makes a distinction. But sometimes you'll see hex written in lowercase like that, and sometimes in uppercase. Doesn't really make a difference. In particular, too, here, because I copied this out of the terminal, you'll notice that the font changed. And I kind of like that, a monospace font when you're working with code look and stuff, because it makes it real obvious that 0 and the letter O are two different things. Okay, a lot of fonts, it's sort of ambiguous there. Okay, so convert all 6 of these into binary. Let me blow up the font a little bit so it's a little easier to see. Okay. Now, when you do this, at first, you probably are going to be looking at that little, the table that I had constructed above, or if you'd scribbled it down, right? You guys are going to get real quick at this, of translating back and forth to binary. Okay, so what is A? A is 10. Okay, what is 10? It's an 8, no 4s, a 2, and no 1s. Right? So eventually this will just become sort of automatic. And then what's 0? 4 zeros. Okay, CE, what's C? Well, that's 12, so that's an 8, a 4, and no 2s and no 1s. And then E is, yeah, 1110 because it's 14, and that's an 8, a 4, a 2, and no 1s. Okay. So good so far? Yeah? All right, C8, well, we've already seen C before, so that's easy. We can just copy the first 4. And then 8 is an 8 and nothing else, right? Let me put a little bit of a space in here just to make it a little easier to read. All right, D. Well, if C is 1100, then D is 1 bigger than that, right? So I just put a 1 in the ones place. And then 6 is a 4, a 4, a 2, and a 1, or no 1, sorry. The 4 is this. We've already run into E. D, we've already run into. And A, we've already run into. Okay, so is that Gucci? All right, and like I said, you'll get much faster at this, translating back and forth between the binary to hex or hex to binary. Okay, and for readability, I often will put a space in between, but not always do you see that space. So in particular, you have to be a little careful on Canvas because whether or not the space is there actually can matter to it. And I've tried in everything to say either do or do not put in the space accordingly, right? To see, because you guys aren't psychic, but just kind of be careful. This is especially, the space, by the way, is especially helpful when you've got just like tons of these things because otherwise it's impossible to read. That's one reason, by the way, that they put the colons in here when they notate it, the thing. I mean, I just copied that out of the terminal just because it makes it easier to read. Yeah, so, okay, good. So, so that's how you move back and forth between binary and hex. And this isn't the only system for doing this sort of thing, but it's the one that sort of is stuck. So back in the day, there was, and occasionally you'll still see it, a system called octal, where instead of going up to 16, we only go up to 8. The advantage there is that then you only use the digit 0 through 7, and you're going 3 bits at a time instead of 4 bits at a time. But 4 bits at a time is kind of cleaner because, well, pretty much everything on a computer is a power of 2 anyway, and 3 is not a power of 2. So, oui, vous avez une question? Mm-hmm. Ah, 0010 would be 2, not 4, because the the powers go up the ones places on the right, then 2, then 4, then 8. That's just the order we write it in. Okay. Good. Okay. Autre question. Uh, okay. Well, those of you guys who are online, if you have a question, just sound off. There is a little bit of a delay, so don't be offended if I blow past you at first. All right. So the next thing I want to do is sort of talk about. So what's going to make a full-fledged computer, right? Like we sort of started with, we talked about a single transistor, okay? And so we were talking about like a single bit or two worth of information on, off for these two wires, that's it. You scale this up to a whole processor and there's going to be billions of these things, right? Do you want to write down billions of ones and zeros? Of course not. Okay, do you want to write down a billion divided by 16 hexadecimal characters? No, of course not, right? So the question is, how do we talk about or measure large quantities of data? Okay, right now we've just been talking about sort of a relatively small quantity of data, but how much was this, right? Well, each pair of hexadecimal characters corresponded to 8 bits, right? So each hex character is a 4-bit sequence. All right, so I've got 8 bits, and then I had 6 of these things, so we have a 48-bit sequence. What else do we call an 8-bit sequence? A byte. Okay, what do we call a 4-bit sequence? This is some good trivia. Okay, so we're really clever, we computer scientists. Okay, so you got a bit, and then you get a byte, and we spell it with a Y just to look cool. Okay, so a byte is 8 bits. Oops. A bit, well, that's 1 bit, right? Obviously. It's kind of silly to even say that. What is 4 bits? Huh? What? Nanobyte? No, sorry. Nope. It's a nibble, right? So you can have a little bit, you can have a nibble, or you can have an entire byte, right? Yeah, I told you we were real clever. Okay, nibble, you don't tend to see that very often. I will use it in probably speech quite often because 1 hexadecimal character represents 1 nibble worth of information because it's a 4-bit pattern. And so 2 hex characters represents a full byte, 8 bits. Okay, why was 8 a good number to pick here as opposed to, say, 10? I mean, we could have picked 10, right? That would have been just fine. So why did we pick 8 back in the day? Exactly. It's a power of 2, right? We're already doing everything as a power of 2 binary counting system. So why not make the units match that? Okay, that's basically it. But then once we've got a byte, right, we want to talk about large quantities of bytes. So what words do we start using there? Well, let's step up a bit. Probably the first one that we could have would be a kilobyte. You guys have probably heard this word a lot. Well, maybe it's been a while. You're probably talking more like mega and giga nowadays, maybe even tera if you're buying hard drives, right? Okay, but the next sort of unit up is a kilobyte. So how many bytes is a kilobyte? There are two correct answers to this question. Yeah, okay. So either what or what? What would make sense here? Okay, I just used the word kilo. Well, what does the metric prefix kilo mean? 1,000. Or if you're old school, and we've got a, there's going to be an ambiguity, and I promise there's a way to resolve that. We'll resolve that in a moment. Okay, back in my day, when I had to walk uphill both ways to school in the snow without shoes, and we liked it, right? Um, it was this. Oops. Okay, it was 1024. Okay, now why? I mean, 1024 is not a number that just came out of thin air. 1024 is a power of 2, right? Yes.
Well, binary, the last is like 256. So.
Right, exactly. Okay, so if I go up by powers of 2, right, I go 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Okay, so that makes sense. It's a power of 2. It's also really close to 1,000. Yeah? Okay, so back in the day, the computer folks were just like, oh, well, it makes sense to talk about things in chunks of 1024 because that's a power of 2. And 1024 is pretty close to 1,000, so why don't we just call that a kilobyte? I mean, yeah, it's not 1,000 in the metric sense, but it's sort of close enough. Yeah, seem reasonable? Okay, well, same thing happens if we keep going up. So what would be beyond that? What would be the next one as sort of a metric if we kept going in powers of, or sort of orders of magnitude of 3 each time? Okay, a megabyte, right? And that's going to be either 1,000 kilobytes or 1024 kilobytes, depending on which system we're using. Okay, does that kind of make sense? And then if we continue this scheme, what would be the next one? Giga. Okay, so and so on, right? So gigabyte is 1,000 megabytes or 1024 megabytes. Um, okay. And then because we can talk about this nowadays, what's after that? Yeah. Okay. And back when I started learning this thing, learning this system, you know, this was in the 90s before any of you were born. Terabyte, gigabyte, no, but I mean, these were like abstract mathematical concepts. You weren't buying any of these things yet. But of course, the computing world being the computing world, you know, can you go out and buy a terabyte hard drive now? Oh, easily. Yeah, I mean, heck, you can get like a 10 or 12 terabyte hard drive, no problem. And, you know, if you want to, what's after terabyte? It's peta, okay? PETA, petabyte. Um, okay. And then after that is exabyte, which, you know, you're starting to get to ridiculous numbers at that point by current standards. Okay, so, um, so yeah, like when I started learning this stuff, right, you were, you know, I remember the very first computer I personally had that wasn't so like the family computer that was sort of dad was in charge of. The first one that I had that was in my room. I had a 500 megabyte hard drive in it. And oh my God, this was the most amazing thing ever, right? Um, and nowadays, 500 megabytes is, an album worth of MP3s or something, right? Um, and that was the entire hard drive for the operating system and all your games and everything. I mean, yeah. Okay, so what are the consequences of this whole 1000 versus 1024 thing? A. And B, how do we know which system we're actually talking about? Okay, so what are the consequences of there being this ambiguity? Let's go shopping, shall we? I want to buy a new hard drive. Let's buy a hard drive. All right, so components. Let's say we want a hard drive. We want a desktop internal hard drive. Say, I'm just making stuff up here. All right, let's pick something. Oh, $50. That looks good. Okay, whatever. So this is a Western Digital 1 terabyte hard drive. Okay, wonderful. How much is actually there? Yeah, well, specifications. Let's read the fine print. And it actually doesn't even say there. Let's look at the specifications. Oh, see, now we're getting into all the nitty gritty stuff where there's footnotes, right? Okay, and let's see what are all the footnotes here? Ah, we blow this up. Actually, let me download it and blow it up real big so we can really see what I'm after here, which is footnote number 1. As used for storage capacity, 1 gigabyte equals 1 billion bytes. That would be, 1,000, 1,000, 1,000. 1 terabyte is 1 trillion bytes, so that'd be 4 factors of 1,000. Total accessible capacity varies depending on operating environment. As used for a buffer or cache, 1 megabyte equals 1,048,576 bytes. As used for a transfer rate, 1 megabyte per second is 1 million bytes per second, 1 gig, blah, blah, blah. Okay, so both systems are in use, and this is why if well, maybe not today, but if I were to buy this thing and hook it up to a computer and then go into Windows, it would show up as like 931 gigabytes. And I'd be like, WTF? I bought a 1 terabyte hard drive and only 931 gigabytes or whatever showing up. Like, I just got ripped off. Yeah? Well, that's because they sold it that 1 terabyte meant 1 trillion bytes. But the operating system was calculating the number of bytes under the base 2 scheme. And there's a discrepancy. Okay, and so hence it doesn't look like it's as big as it is. I mean, it is as big as it is, that nobody ripped you off. It's just that the operating system was measuring under a different system than what they sold it under. Okay, and I mean, nowadays you guys probably don't even notice this sort of thing because, I mean, when's the last time anybody really had to worry about filling up their hard drive? Okay, or maybe you do on like your Xbox, but then you just delete. Oh well, I guess I got to delete Splatoon and put in Breath of the Wild. Well, that's Switch games, but whatever, right? Yes. Oh, well, it's not 2 to the whatever. It'd be 10 to the whatever. Oh, it'd be 2 to the 10th, 20th, 30th, and so on. Yeah. So, yeah, so let's actually go back to my little sheet here for reference. So the question was, let me blow this up. Let me use this just for sake of computation. Okay, so 2 to the 10th is 1024. Okay, so that's sort of the base 2 system, the fundamental chunk, right? And then what was a megabyte? It was 1024 of those. That would be 1024 squared, right? If I had 1024 times 1024, yeah. Well, if 1024 is 2 to the 10th, then 1024 squared is the same thing as 2 to the 10th squared. Well, what happens when you have double exponents going on? Yeah, exponents are like people. When they're next to each other, they add. When they're on top of each other, they multiply. Okay, so 2 to the 10th to the second is 2 to the 20th. Okay, so each time you go up by a word, so kilo to mega, mega to giga, etc., you're going up by a factor of 2 to the 10th. Okay, does that make sense? Oui? No. Très bien. Okay, so yeah, so 1024 is 2 to the 10th. 2 to the 20th would be the number of bits, or sorry, bytes in a megabyte under the base 2 version, and so on. Okay. So there is a discrepancy then between these different unit systems, right? Are we talking the base 2 version or the base 10 version? How do you know? Other than reading the tiny footnote in the product description for your hard drive. Wouldn't it be great if we had a different set of prefixes for both systems so that it would be very obvious to anybody looking at it that there was a difference? Okay. Yes, Mr. Pine. Good question. No. So a gigabit would be that many bits rather than that many bytes. Okay. Um, no, it's actually a way stupider sounding system. Okay. So you know what? Let me make actually let's use Excel because I want to make sort of a table. Actually, you know what? Let's not. Forget Excel. All right, let's go down here. So a kilobyte, so here's the fix. A kilobyte is 1,000 bytes. Use the metric prefix and respect the metric prefix. But I'd still like something to be 1024 bytes. But I can't use the word kilo because that already has metric connotations. So here's what somebody came up with instead. Oops. A kibibyte. All right. Well, let's go up a power. Let me just copy this. So a megabyte would be 1,000 kilobytes. And then a mebibyte is 1024 kibibytes. And then gibibyte, right, and so on. Okay, now, does that sound ridiculous? Yes. Nobody wants to actually say the word mebibyte out loud because it's stupid, but we use it. Now, the Mac operating system, and I think Windows all have done this both relatively recently, they now report things in the same unit scheme that the hard drive manufacturers do. Okay, so for example, the computer that I'm using here, right? If I go to, well, actually, let me do this. Let me go to disk utility. Okay. All right. So Here's the disk utility. 500.28 gigabytes is what it says. On my new one is that's sitting here is a terabyte. Okay, and if I go to Apple's website and look in the sales stuff and look in the tech specs and find the footnote there, it will tell me what that actually is. Okay, in fact, so let's do that for my current laptop, which is like I said, a terabyte. So if we go shopping again, all right, 6-inch MacBook Pro, tech specs. All right, so here we go. Storage. Oh, there's a little footnote. Excellent. So if we go down to the footnote department, blah, 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 blah. Here we go. There. Okay. So actual formatted capacity less, what they mean there are two things. One, when you format a hard drive, some of the space has to get used to basically say, okay, this is the hard drive, and here are where all the chunks are, and how I'm going to put arrange data on it. Okay, but they're using here gigabyte to mean 1 billion bytes and terabyte to mean 1 trillion bytes. And the operating system, right? So if I go to, like I said, that like I did a second ago, the disk utility, did I close it? I must have. It said it was 500 gigabytes. Well, it was 500 gigabytes in the metric sense. Okay, now contrast that to, I'm going to do something a little crazy here. Where is it? Because I'm a giant nerd. I also have Linux running on my laptop, and this will take a minute to boot up. Maybe. It's going. This just sometimes takes a second. Need to put on the Jeopardy music or something, elevator music. Let's see. Let's go to. Nope, there's nothing there. Where did I put everything? Let's go to. Oh, that's right. It's under projects. Here we go. Okay, these files are all relatively small. I know this is probably a little hard to see. Here, it's actually specified exactly the number of bytes because these files that I'm dealing with are relatively small. So I have a C file that was 229 bytes. That's all it took to write some little program. 965 bytes of an assembly source, and then it's 500,000 bytes. So of an executable file. Let me find something that's a little bigger. Oops. Blast. All right, so here's something where I've got some stuff that's a little bit bigger. Okay, and yeah, I'm a little surprised that it's actually not listing it with the prefixes. I guess I don't have anything big enough for it to worry about. Okay, but anyway, the point here though is that at least in Linux, it uses the kibi prefixes. And so, what are those prefixes? As words, we said what it was: kibi, mebi, etc. But nobody ever. So, if I write down a terabyte, what's the symbol for tera? T. Okay, or giga is G, etc. Right. So, what are the symbols for kibi, mebi, and so on. Yeah, ki, mi, ti, etc., etc., right? So hence you might see something that looks like, let me go back to words, it's a little easier to see. You could see, for example, something like that. KIB, okay? Capital K, lowercase I for kibi, 1024, and capital B for byte. All right, what about lowercase versus capital B? That's actually a good, important distinction. Byte versus bits, right? So capital B is for bytes, lowercase b is for bits. And there are occasions where both matter, right? So that's the distinction we use there. Yeah, so the sort of 1024 system, kibi, mebi, etc., is you basically just take the corresponding metric prefix and put an I after it. That's it. Which is relatively easy, right? I mean, we still wanted to kind of like kibi and kilo, right? I mean, these two things are linguistically pretty close, and that makes sense, right? Because it's pretty close to the metric value, so you might as well just keep riffing on that closeness. Okay. Um, okay, but yeah, back in the day, if somebody said kilobyte, you just instantly assume 1024. And I'm old school enough that I still think that way. Um, but you whippersnappers nowadays, so you're in a different world than I was. So anyway, okay. So let me pause and take questions from online in the room. Yes, sir, Mr. Terry.
this, I think it's on subject, but it might be off subject. So when we hear things about like 5G networks, what exactly does that mean?
Okay, the G there does not mean gig. It is not a data measurement. Okay, a 5G network, the G there they're using for the word generation. Okay, and so yeah, 4G, 4G LTE, LTE advanced, right? These are all like, well, okay, some of it's a bunch of marketing BS, but the rest of it, yeah, the G there does not in any way refer to gigabytes or whatever. Now, that said, a 5G network is capable theoretically of transmitting a data at a certain rate to a given device, and that rate, whatever it is bigger than what it would be for a 4G network, which is why it's a better thing, right? Um, and why you're sort of upgrading, if you will, from 4G to 5G networks. Uh, that's not the only reason that AT&T or whoever would want to put up a 5G network, because right, what other things would you want if you were running a cell phone network? Well, you'd want to be able to transmit data reliably to and from a given device. You'd want to be able to connect more devices more reliably. You'd also hopefully like it to be less expensive, power hungry, et cetera, because all of those things affect your bottom line. Okay. Yeah, no, good question. And same thing with wireless networks like Wi-Fi. Um, they the Wi-Fi consortium, which is sort of like an industry trade group that tries to standardize language around this stuff. Nowadays, if you guys go out and buy a wireless networking router, it probably says like it's Wi-Fi 5 or Wi-Fi 6 or something like that. Those are just marketing terms that they made up, right? 5 years ago, if you went and bought a wireless router, you'd be like, oh, well, it's 802.11.AC or .in or whatever, and those refer to specific networking technologies. Now, with a 5G network, right, like I said, there's some number of bytes or bits per second that can be transmitted over it. I don't happen to know what that is, but there's no relationship between the G there and giga whatever. Okay. No, fair question. Yeah, do you have one?
Yeah, so
Sure.
when you partition a hard drive,
Mm-hmm.
like how much storage is acting between like each wall or theoretically?
Depends on how it's formatted. So there are different file systems. Um, there's Windows has several file systems. So this would be the difference between, say, like FAT32, or nowadays, what do you format your Windows drives as? NTFS, right? You also probably are running into exFAT, which is essentially FAT64, but whatever. Macintosh uses a particular file system. Linux has several different. So it depends. It depends on how you format it.
How much storage is that like physically taking up
Uh,
from just from dividing?
well, okay. It's the divisions itself doesn't take up any space. It's how you allocate data to those spaces. So sometimes you waste space, right? If you've got a bucket and you don't use the entire bucket, and you take, like, let's say you've got a file that's 2 buckets worth, but for whatever reason you spread it over 3 buckets, well, then you've wasted some space. Yeah, that's totally going to depend on the file system, um, and which means, FAT32, NTFS, Apple's two formats. See, what is it? HFS, and I forget what their newer one is called. Linux is like ext2, 3, or 4, which are just evolutions of the file system. It just depends. Yeah. Um, yeah. Okay. So to some extent, it also depends on. So, for example, physical hard drives, like the one that we were shopping for a moment ago, was a spinning platter hard drive, right? There was an actual moving disk in there. Well, it's actually more than one disk. So if you cut one of those things open, you're going to see anywhere between 2 and 8, depending, metal discs. They look like, miniature. Well, they look like CDs, right? In 20 years, I won't be able to. CD, man, what's that? Or 8-track record, maybe not 8 tracks, but like, anybody have vinyl? Still listen to music on vinyl? Okay, yeah. Anyway, so there's a bunch of these little metal platters, and depending on how big the hard drive is, you'll have some number of them. Well, if you take your terabyte and you've got 8 metal platters, well, you've just divided that into 8 chunks, right? And then each metal platter is subdivided into which ring you're on, sort of radially coming out from the center, and which sector you're on, which is kind of like an angle from the center. And then, each one can hold certain amounts of data. Um, yeah, now a solid state drive, you don't have that sort of physical limitation because it's just a chip.
That's cool. How did like the lasers work on those?
On a hard drive, it's not a laser.
Oh, SSD is not.
No, there's no moving part. There's no light. There's no nothing. It is literally just a giant chip.
Oh,
Yeah. Now, a CD would use a laser, right? So a compact disc or a DVD or a Blu-ray, uh, there's a surface that has been etched in a very particular way so that when you shine light on it, it reflects it either one way or the other. And then you read that as a 0 or a 1. On a magnetic hard drive, so like the hard drive we were going to buy off Newegg there, you've got this metal platter. It looks like a shiny metal disc, but what really there's um, the sort of magnetic properties of the metal you can alter by running a magnetic field near it. And so to write to the disk, you run basically a tiny little electromagnet that's on the drive head. That's kind of like the vinyl needle that reads on vinyl. And you either turn that electromagnet on or off, and it accordingly writes a 1 or a 0 to the metal. To read it, you just pass the electromagnet over it, and if the magnetic field is one way, it induces a current, which you read as a 1, and if it's the other way, it doesn't, and you read that as a 0. Okay, so it's using basically magnetic induction um, to actually store the data. Um, Solid state drive, no moving parts, right? So your solid state drive and your RAM are very similar in terms of fabrication, with one major difference. What happens if you turn your computer off?
you lose.
Yeah, what's in your RAM if you turn your computer off? Nothing. It's empty. Bunch of zeros. What happens is your solid state drive if you turn your computer off? Data is still preserved. Right? Okay. Well, we'll continue with this on. Oh, let's see. So I did have one. Oh, yeah. Mr. Hargraves asks, where could I get an exabyte SSD, and it's exa, not XO, so that I can have storage for my future children, their children, and their children? Um, Go ask Google. Yeah. All right. Well, I'll quit the stream and see you guys on Wednesday, if not sooner.